V in over V8, 20 over 10, 2. That's just a ratio, so no units. Yeah. And then we simply 2 minus 1 over 2 plus 1. We get a result for Z1 of 166 and 2/3 ohms, to be absolutely precise. Z1 for T-type. No. N minus 1, N plus 1. And then the bottom is 2 times 2 on the top. 2 squared minus 1 gives us a Z2 value of 666 and 2/3 ohms. Okay? So that the values hand calculations give for T-type. A minute. That's 10. N is 20 over 10 still. It's equal to 2. Z1, 2 plus 1 over 2 minus 1 gives a value of Z1 for pi type, 1500 ohms. And this one is 2 squared minus 1 over 2 times 2 gives us 375 ohms. Yep. So that are the values to give you the same attenuation level from a pi type design. Okay. So what we do here is put 166 and 2/3 in each of the Z1, Z3 positions, and a 666 and 2/3 ohms in the Z2 position. We'd have a perfect time half an attenuator with exactly 500 input and output impedance. Yep. Things aren't quite as sweet as that though, because we can't really get our hands on a 166 and 2/3 ohm resistor. Might get lucky, find one in that big box you got down the workshop, but hardly. Ways of getting close to it, but not necessarily exactly. Alright? So that's what the hand calculations say. Okay? Now, what you're going to use with your assignment is a calculator at chimandi.com. Chimandi. Alright? So, keep your values because you're going to need to tell me what they are. Alright? First thing I want you to do, okay, is the next thing you need to do for me is calculate your attenuation level in dB power. So look back in the notes, and I want the attenuation level for that attenuator in dB power. So that's how we calculate the power attenuation required for the calculator. 10 times the log of Vn squared over ZO divided by V8 squared over ZO. In this case, we're looking at minus 6.02 to 3 significant figures, dBs of attenuation. Okay, so again, when you get your specifications, you're going to be needing to use your specified input and output voltage to calculate your attenuation in dB to use this calculator. So at chimandi.com there's a link to their calculators. There are several of them. What we're interested in, you may well find Match and Pi and Match and T. They'll design calculators where the input and output impedances are different. Okay, you could get your results out of them by putting in the same input and output impedance. That will ask for more information than the symmetrical ones that you should use. Okay, a little further down, Pi attenuator and T attenuator, which is the one I'm going to demonstrate. Okay, so there's some terms for you in attenuated networks. In these type of two-port networks, they use the terms series for the series resistors. They use the term shunt for the parallel resistors. All right. So in case of a T, you've got a shunt. You've got a series in, series out, and a shunt. Okay. And then in the Pi, you've got shunt in, shunt out, and a series. Okay. So first thing it wants to know is, what is the system impedance, or ZO? 500 ohms in our case. What's the required attenuation level? 6.02 dBs of attenuation. Once you've given those two pieces of information, the calculator will calculate for you the ideal values of the series and shunt resistors. Okay, now they're slightly away from exactly 2/3 on the end. Why? We got 166 2/3, 0.666 forever reoccurring, wasn't it? And 666.6 reoccurring. Why are these slightly different? Yeah, we're rounded. We've stripped some decimals off the attenuation level. Okay, nothing to worry about though anyway, because we're going to have to go further away from ideal than that to use preferred values. Okay, so that's confirmation that our hand calculations were right. Alright, the next job in terms of using this to design a suitable attenuator as close as possible to that is to decide what preferred values of resistor you're going to use. Okay, now on this page somewhere there is a link to preferred value resistor. Here it is. I'm going to click that with a wheel so I get it in another window. We're looking for our series resistors. We're looking for something as close as possible to 166. Okay, so in our preferred values of resistors, I don't know if any of you are familiar with preferred values, okay, but they're how the values you can buy in a particular percentage tolerance range are spaced so that they overlap each other effectively. Okay, so you've got you've got twice as many resistors in the 5% range as you've got in the 10% range, twice as many again in the 2% range, and so on. Alright, now what Chris does here at the college is he buys 5% resistors because 10% ones are hardly available now, but he only buys values in the 10% range. So he buys half the different values that you can get. There are a few other oddments that you might end up being able to use, but the idea of this is not trying to make the attenuator perfect. It's about seeing how preferred values affect what you get in reality and what you get in terms of simulation. Okay, so if you fiddle around with your resistor value too much and get it perfect, you've got less to talk about in terms of how using preferred values has affected what you actually wanted in terms of your specification and what you actually get in reality. Okay, So we're looking for something about 166. Now, if we look at this here, the figure 100 in there, what that means is you can get a 100 ohm resistor, you can get a 10, you can get a 1, you can get a 0.1, you can get 1,000, 10,000, any multiple of 10 of that figure. Okay? Here, 110 means I can get 110, I can get a 1.1, I can get an 11, I can get an 1100. Do you understand that? That'll do every multiple and divisor of 10 of that figure. Yep. So I'm looking for something in that column around about 166. Now, here I can see I've got a choice between 160, actually I should be choosing from this range, I've got a choice between 150 and 180. Which one's the closest? 150. So just jot that down, we'll use 150 for our series, for our Z1. And then the other value was 666, wasn't it? So we'll use a 680 for that. But that's a first go. If, let's say we were designing an attenuator and we absolutely must not go over voltage into that instrument. If we get an attenuator where the attenuation level is less than what we were looking for, we might come back and adjust one of these values to get it up above 6 dB, because we know we must not go over voltage. Do you understand what I mean? So you might come back to those figures and decide to use the other option because that's a better fit. You might even try all four combinations either side in different combinations just to see which one's the best fit. Okay? So we look at 680, and what was the other one? 150. So going back to our calculator, we can now put in 150 in the preferred value for the series and 680 in the preferred value for the shunt. And then when we click calculate again, it'll tell us the actual dB level of attenuation we could expect from those component values, which is 5.67. So we're actually going to attenuate less with those component values than we would if we had the perfect ones. Okay? And we could go back and try other values for those resistors, either side of those in preferred values. If you really wanted to work on it, you could try putting combinations in series and parallel to get closer to the ideal values. But what you must remember is there's always going to be tolerance involved. Okay, and when the circuit's running practically, that's also going to be susceptible to temperature changes to a certain extent as well. So trying to get these things to be perfect, you're just fighting a losing battle. Okay, so that's not the idea for you to do that. It's for you to have a specification, for you to use this to design, come up with as close as possible design, and then build it practically, and then your tolerances will come into play as well then, because a 100 ohm resistor could be anywhere between 105 and 95 when you take it out of the box. Okay? Any questions about that? What I'd like you to do, right, is go and log on to a computer and have a go with the calculator on the Pi design. Alright, and see how close you can get that in terms of how close you can get to 6 dB with the Pi type design using preferred values. Okay?